Welcome and thanks for watching the video abstract for our new paper on the role of area metrics in AdS CFT. First of all, I'm going to explain to you what are area metrics. You may be familiar with regular Riemannian geometry, where we have a metric tensor that defines a line element, and from that we can define lengths and distances by integrating it along curves. But as a second order consequence of sorts, we can also define areas and volumes and so on. If you only care about areas and you don't want to do the detour of defining length first, you can instead work with so-called area metrics, which take this form. So here we look at these little bivectors, which are spanning infinitesimal parallelograms. They are contracted with this object here, which is the area metric, in order to define what we call the infinitesimal length element, area element. And then by integrating this area element along a surface, you can define the area content of that surface. And from these fundamental equations, you can determine some of the properties of an area metric. For example, the index symmetries here have to be very similar to what a Riemann tensor would look like. In 4 dimensions, you can count here that there are 20 components that can be freely specified, as opposed to 10 components for a regular metric, meaning that this is a generalized notion of geometry. Every metric implies an area metric, but not every area metric is implied by a regular metric. In those specific cases where the area metric is implied by a regular metric, this relation here holds. And now in physics, this idea has also been studied a lot. There's a large body of literature, especially by Schuller and co-authors. What we are going to do is we're going to look at the linearized approach to look at linearized area metric fluctuations around a fixed metric background. So we have this kind of decomposition here, where we have an area metric, which to the 0th order is given by a metric-induced area metric. You remember the equation from the previous slide, plus an area metric fluctuation, which is infinitesimally small. And this area metric fluctuation in terms is split in 2 parts, one corresponding to a regular metric-like fluctuation, accounting for 10 degrees of freedom, and one being the purely area metric-like fluctuation, which accounts for 10 more degrees of freedom and satisfies these properties. So in addition to the properties of a general area metric, this also has to be traceless, making it look a little bit like a Weil tensor. So this is essentially what we are working with. But what is our motivation for looking at this? Interestingly, in physics, there seem to be a lot of different directions from which people arrive at this concept. People from string theory, loop quantum gravity, second order geometry, and entropic gravity. What's interesting to us specifically is that area metrics may describe space-time superpositions or ensemble averages of metric geometries. Also, our background here is one of AdS CFT and holography. So oftentimes there one gets the sense that area is a more fundamental concept than length, for example, in all these entropy bounds. A perfect example of that is the Ryo-Takanagi formula, which is kind of a generalization of the black hole entropy formula. So to give you a brief introduction, in AdS CFT, we oftentimes have this kind of AdS or asymptotically AdS bulk spacetime, which we call the bulk, which has an asymptotic boundary on which a dual quantum field theory, a CFT, is assumed to live. Here I give the line element of AdS in a usual coordinate system where z is an inverse radial coordinate. So the boundary is at z equals to 0 here. And because the CFT is a quantum theory, if you take a little subregion of it, you can define the so-called entanglement entropy, which is a measure of quantum entanglement between that region and its complement. And via the Ryo-Takanagi formula and holography, that is encoded in the surface area of a given extremal surface that lives here in this curved bulk geometry. So here again, the concept of area seems to be much more important than the concept of length. And thus it becomes very, very crucial and interesting for us to understand what happens if the bulk geometry is just given by an area metric, not a regular metric. Clearly, this equation can still be defined, but what are the consequences of that? So the second motivation for us is that in AdS CFT, those states of the CFT that have a nice description in terms of a bulk geometry that satisfies Einstein's equation and so on are actually special. They only form a subset of the space of states. So by introducing a generalized notion of geometry, like area metrics, our hope was that we would also be able to apply holographic techniques to a larger subset of the space of states. And so the question becomes, can holography lead to a generalized notion of bulk geometry beyond this Einsteinian paradigm? So this is the motivation that drives us. And with that, I can tell you what in this exact holographic approach we were able to achieve. What essentially we follow in the footstep of these very important papers here, which came out more than 10 years ago. What they did is to rely not only on the Ryo-Takanagi formula, but also on something called the first law of entanglement. Keep in mind the dual theory is a quantum theory. So if you perturb the quantum state of that theory a little bit infinitesimally, you have this relation where the change in entanglement entropy is equal to the change in the expectation value of the so-called modular Hamiltonian. And this equation is very interesting and useful because the modular Hamiltonian can be related to the expectation value of the energy momentum tensor of this dual quantum field theory, while via the Ryo-Takanagi formula, the change of entanglement entropy is sensitive to the change of the bulk geometry. And so from this simple relation, these papers were able to derive two major statements. First of all, the holographic dictionary, meaning the exact formula that you can use to read off the value of this expectation value from the shape of the bulk geometry. And second of all, Einstein's equations at least linearized around the background AdS spacetime. Our goal in this project was to do the exact same, following the same footsteps, but with generalized area metric fluctuations in the bulk, not just regular metric fluctuations. So our two main results are these. For the dictionary, we find this equation here, where you see we have these metric and area metric-like fluctuations, which have to have a certain asymptotic behavior towards the boundary in this set coordinate system. So here the leading order has to be set. Here the leading order has to be of the form 1 over set. And then you can read off this kind of leading order term. And this combination here gives you the full holographic dictionary. Furthermore, we were able to derive the equations of motion. And in addition to Einstein's equations, which we just write down as E menu here, we were able to derive this correction term, which depends on derivatives of the area metric fluctuation. So this is very, very interesting. And of course, now that we have an equation of motion, the question becomes, can we find bulk Lagrangians that give rise to these equations of motion? And this is actually very simple to do. So from the perturbative Einstein action, we get Einstein's equation. To this, we add this kind of coupling term here, which gives us in this equation exactly that correction term that we had derived. However, in this Lagrangian, if you want to treat both h and w as fundamental variables, you also have to take the variation with respect to w, and that gives you a second equation of motion. So here, the term coming from this coupling term is going to be linear in h, and including second derivatives. So this can be written as the first order change of the bulk Weil tensor due to the metric-like fluctuation h. Of course, to this Lagrangian, you can also add terms that are of square order in W, which we parameterize like this. And from these, you get also, of course, terms in the equations of motion as such. And so this is very interesting. A few comments. In this model that we are using, we have three parameters, m squared, k1, k2, which interestingly are not specified yet by what we have said so far. However, this we believe this will be possible in the future by doing a procedure called holographic renormalization. What you should know is that we have derived this entry to the holographic dictionary from the first law of entanglement. But the usual way for a given Lagrangian to derive the holographic dictionary in AdS CFT is this holographic renormalization procedure. And we expect that for just random values, m squared, k1 and k2, the result that we get from that is not going to be consistent with the result that we have derived from the first law of entanglement. So demanding consistency between these two results, I think, will allow us in the future to constrain these terms more stringently, and that will be a very, very interesting thing to do. The whole procedure is a little bit complicated, so we leave that to the next paper. But we were already able to carry out the first step in this direction. Namely, if you remember, for this holographic dictionary that we derived to work, I told you that this field W has to have a specific asymptotic behavior near the boundary at z equals to 0. And for generic values of m squared k1 and k2, the equations of motion here are not going to allow for solutions of that form. So demanding that this is the case already allows us to constrain one of these parameters. There's a different problem that arises. If you look at these equations of motion, you may be tempted to just, for simplicity, set W equals to 0 again, going back from this exotic area metric-like geometry to the regular Einsteinian or Riemannian type of geometry that you're familiar with. If you do that, these terms here drop out, and you're left with two equations that are two conditions for H. One being Einstein's linearized equations, the other one being this change of the Weil tensor. So for this set of equations, only those solutions, H menu, are valid solutions that satisfy both Einstein's equations and which are conformally flat. And that's kind of interesting because it means in this limit where we go back to Riemannian geometry, we do not reproduce Einstein's equations and their full set of solutions. Especially a lot of really interesting solutions that we usually work with in AdS CFT, like black brains, for example, would not be allowed as solutions to this set of equations anymore because they're not conformally flat. So that was a bit worrisome to me, and I think it's very interesting. So we tried to find a way around that conclusion. And one way to do that is by introducing so-called Lanczos potentials. So as you may remember, the Weil tensor can be written in terms of derivatives of a Lanczos potential. And in fact, it was shown that any tensor of this form can be written in terms of such a potential by its derivatives. This equation here is very involved, but we were able to handle it. And now we were able to write down an ansatz for bulk Lagrangian of this form. So here we have this perturbative Einstein action. We have the same coupling term as before, and we have this term here. In terms of W, that would look like a mass term. But keep in mind, everywhere where W shows up, we expect it to be expressed as derivatives of the Lanczos potential. So this is actually a kinetic term now. And if you take the variations of this action, the variation with respect to H gives us the same Einstein equation plus correction term, again, that we had derived before. So this is consistent with the first law of entanglement. The variation with respect to this Lanczos potential gives us this equation here, one term coming from the kinetic term and one term coming from this coupling term. This term here, for the moment, I just call F. If you derive it in a brute force manner, it's very ugly. It is linear in H and includes third-order derivatives. But if you simplify it a little bit and, for example, commute covariant derivatives in the right places, you will be able to show that this can be written exclusively in terms of derivatives of Einstein's equations. And this is interesting from the perspective that I just explained, because if in these equations we set W or L to 0, and we go back to the concept of Riemannian or Einsteinian geometry that we are familiar with, here we are left with linearized Einstein's equations, and here we are left with this term being set to 0, which is, of course, redundant, because if Einstein's equations are 0, then this is automatically 0. So this bulk ansatz does fully recover Einstein gravity in the limit of Einstein geometry. Furthermore, as I said, it has to be important that this asymptotic behavior of the area matrix is allowed, and this can be verified that this is indeed a possible solution of these equations of motion. So this is also a nice consistency check for us. And that concludes the scientific results that I wanted to share with you. I have two announcements. First of all, if you are, if you're looking for a job right now and you think that area metrics are very, very interesting, I absolutely invite you to apply to the postdoc position that we have open in our group. The deadline is the 5th of December, so not too much time left. Second of all the mathematical files that are necessary to kind of reproduce and check our calculations are publicly available on the repository of Jagiellonian University. So you may have a look at that. You are very welcome to do so. And with that being said, I would like to thank you for watching and also recommend you to have a look at these very interesting papers that I referenced here. Thank you.